All right, okay, so today we're going to jump into something a little different. We're still doing time series, but we're going to do the first of two lectures that are going to talk about non-parametric approaches to forecasting from time series. I'm going to talk about exponential smoothing, and then Eric's going to talk about EDM, which is a different approach. Okay, so exponential smoothing is, so it's a non-parametric approach. We're not going to be fitting a model, not like we're fitting a REMA model and we have this underlying model for the data where we can say, you know, X equals something plus error, and we could, you know, forecast from that model. So with so that's a parametric model. Exponential smoothing has no real model underlying it. It has an approach, but it's not a statistical model. So let's start off with a really, yeah?
Your slides aren't changing.
My slides aren't changing.
Okay.
Is it changing now?
I had no idea that you were one step behind. Okay, you're good.
Okay.
Back one.
Okay, great. Okay, let's start off with a really simple exponential smoothing model. So simple, you actually wouldn't think of this as an exponential smoothing model, but it's a type of exponential smoothing model. So one type is to say that the forecast next year, so let's say 1988, our forecast for 1988 is just the value that we observed in 1987. And we could write that as this, as 1988 is some weighted average of prior values. And we just happen to put all the weight on the last value and zero weight on the values before that. So if we saw this graphically, it would look like this. So this is our weighting function. This is the weight that we put on prior values. And here are our prior values. We're trying to forecast 1988. So we're going to put all the weighting on 1987 and zero on everything else. So that might seem, well, that's a little extreme, right? Because that's saying that none of these values have information that might help us forecast 1988. So maybe it would be better to put a little bit of weight on these prior values. So we could do something like this. So we could have this be our weighting, and then we're going to have it fall off, exponentially fall off. And now our forecast is going to be an average of all these prior values, but we're going to weight by that function. So this is the idea behind exponential smoothing, is that it's a smoother, so that's like we're taking an average, but it's exponential smoothing, that the weighting that we're putting on past values is falling off exponentially. The parameter that we estimate for an exponential smoothing model is how fast these weightings fall off. So that parameter is typically called alpha, and if that alpha is 1, you get to the naive model where you put all the weight on the last time point. Alpha is 0.5 is kind of like that. And then as alpha goes to 0, it's like putting an even weighting. And if you have an even weighting, what that says is your forecast is just the average of everything in the past. So those are the two extremes. Either our forecast is what we observed the last time step, or our forecast is the average of all our data. As you'll see, one of the nice things about exponential smoothing models is, one, we're not making any assumptions about our data. We're just smoothing our data to make a forecast. But the really nice thing is that as our data change, our forecast follows our data. Okay, so what that means is if your data at first, let's say, here, let's say this is time, and I'm going to plot out kind of what my data look like. So at first, my data are kind of going like this, like that. Well, your forecast is going to be this weighted average of the past, and it's going to be nicely kind of just forecasting right about there. And it's all of a sudden your data change, something drastic happens, and they start going up like this, like that. Your forecast is just going to naturally evolve. And after a few data points, it's going to start tracking, and it's going to be forecasting upward and upward. And it's not, and eventually, depending how much weighting you put on things, it's not going to care about this flat part. It's just going to be tracking the new data. It's just going to keep evolving. So that feature is really nice where you have data that don't have this kind of strong, consistent pattern to them. So, for example, what would be a strong, consistent pattern? So if all your data came from an AR1 with a particular AR1 parameter, and it was always like that forever and always, great. You estimate an AR1 model, and you forecast from that. But what if your data, they just kept changing, and they kept changing, and they didn't follow any particular pattern? It would be nice then if your forecast would evolve with your data. The forecast package makes it really easy to fit this class of model. And the function in the forecast package is ETS. And basically, you just pass in your data, and then you're going to have this argument that's called model. And then if you do question mark ETS, you're going to see it has a million other arguments. We're not going to care about all those arguments for now. Let's just focus on the first two. Okay, so this one, the model, is a really important one. The model is 3 letters. The first letter is referencing the level of the model. So are you going to, what I've been showing you so far, you're just modeling the average level as an average of the past. But I didn't add in there any trend. So like if so for example, if the data were tending to go up like this, you probably wouldn't want to just have the past value, right? That would just be going across like that. You probably want to say, oh yeah, wow, it's tending to go up. I want to start from here and go up here. But you'd have to have a trend in your model. If you didn't, you just keep kind of going like that. So the second letter is if you want a trend in your model. We're going to see that in a moment. We're going to start with this, with just the level. And then at the end of the lecture, I'll talk about the third letter, which is modeling the seasonality. Okay, so those 3 letters, we're going to start with just the first letter. And then there are actually 4 possible values. I gave you 3, but there's a 4th one. Z is choose the type of model to use. A is an additive model. So that's what I've shown. You take these weightings, or like you take the average of all the data. That would be if your alpha is equal to 0. But just like you could have you can have an additive average, or you can have a multiplicative average. You can do the same thing with ETS models. So that would be like, you know, multiplicative average. You take 3 numbers and then you multiply those numbers together and you take it to the 1/3. So it's that kind of idea for multiplicative. And then the fourth one is if you say it's in, that would say don't include that in the model. So if you have in for this and in for that, it's saying only include a level in the model. So we're going to start out looking just at level exponential smoothing models. So we're going to have, we're going to start with non-seasonal models, and I'll show you the trend and the ones with the trends and the ones with just the level. So for the level only, it's you want to have 2 ins, an in for the trend and an in for the season. I'm just going to talk about additive models. Multiplicative looks exactly the same. You just put an M there instead of an A. And then when we do the trend, we'll have additive, additive, and then no season. If you read the information in the forecast package, or you go to the Hindman book on forecasting, he's got a long section on exponential smoothing models, and he'll talk about all the different variants. These models have a long tradition. I'm going to show you today just a small subset of them, the easiest subset. And the alternate functions there, because these are famous models, they have some shortcut functions. In particular, the one with trend. Very well known. It has a name named after the person who popularized it, Holt. Okay, so let's see an example. So we're going to look at the anchovy data that you've worked with before. Greek landings, but it's the same landings data set that you're working with. We're going to look at the same time period, so it's the anchovy. Let's look at years 1997 and earlier. We're going to make it into a time series object starting in 1964. So that's when the data starts. And then once you do that, once you have your data set up, fitting an exponential smoothing model is as simple as this. Pass in the data, you specify which smoothing model you want, and then you can do a forecast. Exactly the same way that you were doing with the ARIMA models. And the output should look familiar. So I said we're fitting a model without a trend. So it shouldn't surprise you that the data are flat. That's how they should look. And it's using the weighted average of the prior data. So that's why, like, each forecast is going to be the same because it's using the same weighted, the same averages and the same data points to average. But what changes is the uncertainty. If you look at the estimates that come out of the fit, here's that alpha. And using that, you can plot what the weighting function is. If you go into the RMD file, it'll show you the equation for the weighting function that ETS is using if you look at the help file. So you can see that it's estimating that the best forecasts are coming when really only using, what? 1, 2, 3, 4, really only the last 4 data points. And then after that, it's indicating there's not any extra information in the time series about the level. Okay, I'm going to skip that. Okay. All right, so let's talk about an exponential smoothing model with drift, or with a trend. Okay. So all right. So if you fit a ARIMA model that was a random walk, so this is your random walk, so it's a 0, 1, 0, and you said include drift. That model would be the same as using the last data point as your level, so the average level here, and then it would include a trend that would be the average trend over all this. So when I say average trend, what does that mean? If you took these differences, so this is how much it went up or went down within each pair. So those are all the 1-year trends. You took the average of that, that would be your average trend. If you don't have any missing, well, in case even if you have missing values, but if you have a time series like that, that just works out to being the end minus the start divided by the number of transitions. Okay, so that might seem a little extreme, right? So we're using only the last data point for our level, and then kind of strangely for our trend, we use the average of all our data. And it might make more sense is if we could do the same thing with the trend that we did with the level. So instead of just using instead of using the average of all the trends in the data, if instead what we could do is use more recent trends, put more weight on those. And so that would allow that you see here, things are kind of flat, and then they start going up more steeply. And so what we would like is that our forecast uses this information where we have these steeper trends, and so we would have a steeper trend here. You kind of see how this blue line doesn't quite seem to match the more recent data. Like if I were to like visually do that, I'd want it to be up like that, right? Just to match the more recent data. Well, what's going on here is like, yeah, it's a little steeper here, but it's a little flatter there. It's taking the average, so it's halfway between. Well, exponential smoothing allows us to weight the more recent trends. Okay, so let's see this. Okay, so this here is a plot of the first difference of the anchovy data. So these are all, going back here, all these 1-year trends. So this one is going to be positive, this one's going to be less positive, that's going to be pretty positive, that one's going to be negative. So that's all I'm plotting here. 0 is no change. So anything below here is a decline, and anything above here is an increase. So as I was pointing out, like this one had a pretty big increase, this one had a lesser, then we had another big increase, and then the time series went down. Okay, so these are all those trends. This is the average over the whole time series. And what we'd like to do is to put more weight on these See all these positives here? I'd like to use all these positives and maybe have a little bit higher trend. And that's what the exponential smoothing does. Exactly the same way that we're doing for the level. Now we're going to weight those trends. And it's going to, what we're going to select is how much weighting to put on those past trends. So I showed you that random walk with drift, and I said that what that does is take the average over the whole data. So what that random walk with drift is doing is it's basically like the red line. The parameter is called beta for this. So it's basically like a beta of 0. Now with exponential smoothing, we can say, well, we don't want to do just that. We want some other options. Well, we could have a beta of 1. And if we had a beta of 1, go back here, it would use that trend right there. So what it would do is say, it would estimate kind of what the level should be. So the level would be kind of like if I were to forecast without a trend here, what it should be across this way, which would be somewhere in here. And then I'm going to say, okay, what should the trend be? And if I had a beta of 1, I would take a nice steep slope like that, and I would end up here somewhere. But that might be a little extreme, right? So maybe I shouldn't just do that one. Maybe I should take that average of that one, and then use a little bit of that, use a little bit of that, and weight those exponentially. So, for example, if we had our beta of 0.5, we would weight the most recent trend most heavily, but we use a little bit of information from the trend before that, etc. It falls on. Okay, so that's the math. We can skip that and jump right here to look what that forecast looks like. So here's how we fit that model with ETS. We now have an A for the level. We have an A for the trend. And then we just do ETS. And then we can do our forecast. And now you see it's estimated a trend. So now this is going up. The nice thing is that if the data change and it starts going like this, our forecast is going to evolve, and it will have the trend go down as this trend changes and this trend goes up. It really doesn't matter what the data do. Our forecast is going to evolve as the data change. And this is a really nice feature of exponential smoothing models when you're doing automatic forecasting. You're not looking at the data. You have the data coming in, and then you are basically running this code as the data come in, and your forecasts just keep evolving as your data change to wherever they change to. So what I mean is like whatever level it goes to, however the trend changes. Yep.
For the AAN or the AHN, like, do you define what, like, could you change it from beta of 0.5 to like 0.7 or or does it automatically?
You can specify what you want to use. I'll show you an example of that when I show a seasonal model. But when you fit it like this, it is finding the optimal beta for you. It's doing, that's the nice thing. It's computing what that optimal is. And I find it useful to look at, where's that output? Come on. Look at the output from the fit and take a look at what this alpha is. And then I like to then, plot that out so I get a sense of, okay, how much, what does an alpha of 0.7 look like in terms of the weighting function. So I'll plot it out, just get a feeling for how fast that's falling off. Oh, thank you. 0.7 falls off pretty fast. And it's using yeah, it's fitting these with a well, it's kind of interesting. You can translate this into a state space model, and it but it's essentially it's like it's it's using essentially cross validation to choose those. So it's doing a one step ahead forecast and then comparing that forecast with the actual. That's in essence what it's doing. The actual algorithm is it translates it into a state space model and uses the Kalman filter to, or something similar to the Kalman filter to fit. Okay. Okay. So another nice thing that you can do is you can decompose your fit, and the autoplot function under fit will do that for you. This is the raw data, and then this is your level, and so it's showing how the level estimate is changing over time. And then I think this is the one that is particularly interesting, which is this is that estimate of the trend that will be used in the model. So let me actually back up a little. I should show you this math here for a moment. So this is how the exponential smoothing model is modeling your data. It's got this level term that it's going to compute, and then it has this trend term that it's going to compute. And when I say compute, it's computing from those weighting functions that we saw. It's just a weighting of the past values. When you do the decomposition, it shows you what these two are. And the trend one is kind of interesting because this is its estimate of the smooth trend that gives the best forecast. And so what you're seeing here is basically what you can see by eye. This is going negative here, so there's a short period where the trend is negative, and then generally it's more positive. And you can see here what you saw by eye, which is that trend is more positive here. It's going up in the general faster in this part of the time series than in this part. You wouldn't use these directly. It's more to just kind of get a visual sense of what the model fitted is doing and kind of what's going on in your data. These little things here are to visually cue you in that the y-axis scale is different. So that's all that is. Okay. Any questions about exponential smoothing? Simple exponential smoothing. Okay, you good? We're going to play around with this in the lab, fit these kind of models, and compare them to a bunch of different types of models. And speaking of, yeah?
I was saying, one interesting comparison with these exponential smoothing models might be to some of the like Gaussian process or spline type, like a GAM type model, which is doing kind of similar things, but the spacing and the covariance functions are just going to be different. So
yeah,
some of those are not as automated as this is, but I think you can get similar behavior with like a Gaussian process model if you have a lot of, I guess if you have a lot of, it's not, but we can talk about that more next week or in the lab.
Yeah, no, I think that would be definitely interesting to compare. I think that like if you had, okay, so with the with exponential smoothing model, you don't keep estimating what is the best weighting function. I mean, I guess you could, but you don't have to. So you could just you estimate one weighting function, and with that weighting function, your trend estimates are going to keep evolving, and your level estimates are going to keep evolving. With a GAM, I think my intuition is you'd have to keep. I worried you might have to keep estimating the knots, or you have to be careful that you don't have too few knots, because when the data starts getting kind of wiggly, I mean, you could have the same problem with exponential smoothing, but my intuition is that might be more of a problem with GAMs.
Yeah, and with a GAM, like a GAM, you don't want future observations to affect the current one. You want previous data to affect forecast, but not the opposite. So putting some control on that would be important.
Yeah. We'll see if I'll try to put in some GAM examples for the lab on Thursday when we're doing model comparison. Okay, so let's talk a little bit about validation of forecast. What we've been talking about in the previous weeks is we're basically measuring the fit of the model to the training data. So like when we're computing AIC and AICC or BIC, anything like that, or, well, leave one out, cross-validation is not exactly, that's different. But definitely all those information criteria that we're using, we are fitting the model to the data, we're getting the likelihood, and then we're using that likelihood to compute some metric. So either it's AIC, BIC. That's a fit of the model to the training data. And now what I'm going to talk about is out of sample forecast. So we have some new data, and we're going to make a forecast for that new data. So it's not a fit. So we're not using any of the data we're going to test against to fit the model. That's the difference. So here's one common approach to this, and that is to hold out some test data. So we are trying to build a forecast model for anchovy, and we hold out a couple years. The paper that I referenced when I was talking about the anchovy data, the 1996 paper, this is the approach that was used. They held out these last 2 years, and they tested all the models against these last 2 years. So with that approach, what you do is you fit your model to your data. This is our training set. And then we're going to make a forecast. These blue points are point forecast, and the red triangles what actually happened. All right, so they're different, but now we need to quantify how they're different. And there's a whole bunch of metrics out there. Here are some common ones. So one is just the mean error. Let me go back a little bit. You're going to see a bunch of code, and it's going to say ERR, which is error, and that error is just these two differences. Difference between this, and the difference between that and that. In general, I could have mini forecast, and all those errors would just be the differences between the forecast and the actual data. Okay, mean error, simple, just mean your error. Root mean squared error, take the square of your errors, take the average, the square root. This is the one that I see the most. Mean absolute error, you take the absolute value of those errors, take the mean. These, I don't see as much, but I think in other literature you see them more often. The percentage errors. So you just take the percentages relative to the data, and then the absolute percentage errors. So in this case, what we're seeing is those forecasts here, they look pretty far off, but the average is only, the difference is only 3% of the average value in this time series. Doesn't seem that big, although there's probably a lot of, if I converted that to actual numbers, that would actually probably be a lot of anchovies. Okay, so nice thing about the forecast package has this function called accuracy, and you can feed it a forecast from any model, feed it test data, and it will print out two numbers. The first one is within your training set. We can, well, okay, so what's going on in that training set is it's doing a bunch of one-step ahead forecasts, and it's, but it's using, it's fitting the model to all the data, and then it will use, takes that model and then looks at, say, the first, 2 data points, makes one forecast, compares to what actual, there's 3 points, make a forecast, compare. But it doesn't keep re-estimating the model with these like longer and longer time series. So that's what's happening in the top. The second one is it's just doing the comparison, in this case, of the two data points, those 2 blue points, comparing that to the red point. So it does that, and then it spits out all those metrics for you. So it saves you quite a bit of work. How do you use that? So typically what we would do is we would have a candidate set of models, and then we fit all those models to our training data, and then we make forecasts and we compare them to our test data. So here's an example. I'm just going to take 3 models, a model with first difference and an MA, a moving average, and this is a first difference with AR1, and then this is the naive model, which is just using the last value observed as the forecast. And then you can make a table like so. So this is the sort of thing that people would okay, so that that's not actually many tests, right? So we just left out 2 data points. So we're sort of judging our model just based on 2 forecasts. That's not very satisfying. The other approach, well, okay, not the other approach. So you might think, well, I'd really like a lot more tests. But the problem is that the more data that we leave out for testing, the less data we have for fitting. And data is precious. We don't want to leave data out. So another approach that people take is cross-validation, time series cross-validation. There are 2 variants of this. The first variant is this sliding window. And this is how it works. You take your data set. So here's our anchovy data set. And we're going to make 9 forecasts. we're going to say that we're going to have at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're going to have 11 data points to fit our model. So we set that up. And then we're going to fit our model to these. Okay, so when I say fit our model, what do I mean by that? So in that previous slides, I showed one candidate model was a first difference with a moving average lag 1. So that would be a model. So when I say I'm going to fit the model, I'm going to fit a ARIMA 011. I'm going to fit it to the black points, and I'm going to make a forecast. So I've got one forecast. Add one data point, I'm going to fit it to those data, I'm going to make a forecast. And I just keep doing that. So now I have 9 forecasts. And I compute those same metrics that I just showed you with the forecast. So for each of these forecasts, you can imagine I could have the real data. I'm not showing it, I'm only showing the forecast, but there is a real data point there that I could compare to that red dot. All right, so the, well, some people don't like that because the amount of data being used to fit my model keeps changing. And if that bothers you, then you could also use a fixed window, so fixed window length. So now I'm using a fixed window length, but I just keep sliding it over and sliding it over. And still I have 9 forecasts, but I'm always using the same number of data points to fit the model. Okay, so those are 2 standard approaches for doing that. The forecast package makes it really easy to do this. It has this function called TSCV. And I'm going to walk you through this because we're going to do this in the lab. And it's the first time you play with it, it's a little bit hard to wrap your head around. Okay, so what this function takes, this TSCV, it takes your data, that you've got your training data, and then it takes a function that creates a forecast. And then it has these other arguments that will go into this function. So if this function had no arguments, and I could have written it that way, nothing would have appeared here. If you've ever written functions for something like Optim in R, it works exactly the same way. Or anytime you have a function that takes a function, it will have this format. Okay, so what this wants is it wants a forecast, and it wants the function that creates a forecast. So let's see how that function would look if I want to fit a ARIMA model. So here's the function for fitting an ARIMA model to some data. And it's going to keep creating these chunks of black dots. Those are going to be your X. And you've got to write a function that can take these X and produce that. Okay, whatever X you throw at it, that is what I've just written right here. These are my black dots. Here's my function. Tell me the black dots. I'm going to fit an ARIMA of order, whatever is specified here. It's going to be 0, 1, 1. And then I'm going to take that fit and I'm going to make a forecast. Okay. So let's see here. Okay. So what I'm going to show you now is I'm going to do, okay, I did the sliding. Okay, so I did this one here. I'm going to fit that ARIMA 011 to the anchovy data, and I'm going to use this strategy, the sliding cross-validation window. Wrote that function, I fit it with TSCB, and now these are the errors. So what this spits out is it just spits out the errors for those 9 forecasts. And then, it's kind of, this is a bit annoying with this function. You have to compute your the metrics for the errors. So I'm just going to compute 2. I'm going to compute the root mean squared error and the mean error. So it's outputting the errors, so the 9 errors. So the root mean squared error would be the errors squared, and then square rooted, and then the mean would be that. I had to put NA equals, NA remove equals true, because this will, it'll have some NAs in the beginning of it. When I don't have when I don't yet have that many data points, it's going to be NA until I get enough data points, and then I'll have the errors. Okay, so let's just see a comparison. So this is what I would get if I used time series cross-validation, and this is what I would get if that thing where I was talking about how far out in the future you forecast. So that is this situation visually. So a lot of times, or sometimes, what people want to do is they want to look at forecasts that are farther in the future, and that might be in a fisheries situation. Think about like you're trying to forecast catch, and the data that you get from the government agency is always has a 6-month lag or a 12-month lag, right? Because it's not like they're out there doing the surveys, and then the moment that survey is done, they're like, there's your catch estimate. It doesn't work that way. You got to process that data. It takes time. So there's always this lag between when you get the estimate and when you want to make the forecast. Sadly, these lags can create your forecast can be a lot poorer if you have lags, and the more significant lag you have, the worse your forecast will get. We'll talk on Thursday about how people try to get around that by using a covariate. So in that case, what you're trying to do is you say, okay, well, I can't get a catch estimate, or I've got this like 12-month or 6-month lag, in my catch estimate. But I know what these covariates are right now. Like, let's say you're using sea surface temperature, right? You get that instantaneously, and so you don't have that lag. So maybe you can improve that forecast if you could use the covariates. Okay, so right, those are some. Okay, so I just briefly show you how this works for time here. Okay, the ETS models exactly the same as for the ARIMA models. Okay, here's our forecast for the ETS. This is the one with the trend. We use the accuracy. So in this case, do I have the forecast? Okay. FR is the output from, if I did, the code would be FR equals forecast fit, whereas where fit is what is output from ETS. So it would be fit equals ETS data and model. So format is exactly the same. It's one of the really nice things about using the forecast package is you can fit all these different types of models, and then the helper functions are the same for all of them. Same with the TS function. We can do that time series cross-validation, but now that function looks a little different, right? So we need to write this function that is going to output a forecast. And now our model that we're going to fit is going to be an ETS model. So our function looks like this. Our X, that's those black data points. Okay, we're going to take whatever data are given. And now we're also going to take the H, how far in the future we forecast, and then model. And then here's the function. We just take the ETS, and then forecast fit. So that that's a function that will output a forecast from fitting an ETS model. These things appearing here are those arguments for that function. And now model has to specify an ETS model. So what I'm saying is fit a ETS model with a level and a trend. Okay, and as I said, it's outputting the errors. It's, I see, I should have specified exactly what the minimum length of time series is. It's just using the default, which I'm guessing, looking at this, since it goes all the way up to like 25, that it's using at the minimum like 1 or 2 data points. Whereas when I was showing you those figures, that's what's going on there. It's something you can adjust for your for that function. Okay. Let's see. Okay, so I showed you that. Okay, let's see the time here. I want to jump and show you some seasonal exponential smoothing models. All this stuff with the forecast accuracy metrics, exactly the same for the ETS models versus the ARIMA models, which I showed you before when I was demonstrating the accuracy metrics. The reason it's all the same is it's just using the errors, the difference between the forecast and the actual data. In the lab, we're going to put all this stuff together, and we're going to be comparing performance in candidate sets of models. So we're going to do things like this. So we're going to be looking at exponential smoothing model with trend, exponential smoothing model with no trend, ARIMA models, different selection of ARIMA models. And we've selected this set, using those examples that you saw when you were learning about ARIMA models. Remember when you were using auto ARIMA and it was showing you the different models that it was fitting, and you could select all the ARIMA models that were within the AIC of 2. They're all kind of fitting the data. Similarly, you develop those sets. Okay. So what you're seeing here is that this is all using the forecast package, and how you can very easily, just with a few lines of code, create these candidate models and create forecasts from each candidate model. And once you have those forecasts, you can use these tools, these cross-validation tools, to test your forecast and then help select your models. What we're going to see in the lab is how, if you select your model just based on model selection criteria, so that's saying how well does this data fit my training data, you'll see that you can come up with different best models than if you did something that said, use some type of cross-validation where you're trying to predict out of sample. And in particular, you'll see that when you start trying to make forecasts out into the future, you're really going to, you'll find that quite different models are better at making long distance forecasts than the ones that fit your data the best. And it has to do with the penalty of estimating extra parameters starts getting higher and higher the more you try to forecast out into the future. Okay, in the last few minutes here, let's see seasonal exponential smoothing models. So here's our Chinook data again. Okay, this is what it looks like. Okay. So remember from our seasonal lecture, fitting seasonal ARIMA models, ARIMA models didn't have any trouble with these missing data. They just plugged right ahead. And the reason is that the ARIMA model has a process model. It can produce the expected value of that, what the estimated error is around that, and just kind of chug along. But an exponential smoothing model doesn't have a process model. So when I have a gap there, I'm stuck because my forecast is based on the average of past values. So that's a downside with the exponential smoothing model. You can't deal with missing values. If you just had, 1 or 2, you could do something like interpolate. Wouldn't be that bad, but definitely big gaps like that, problematic. So what's going to happen when we fit to the Chinook data is ETS is the function is going to search for the longest string with no missing values, and it's basically, do we have any missing values? Yeah, it's basically going to pick that string right there, and it's going to ignore those data there. Okay, so now we're going to fit seasonal models, and now we're going to use the third letter here, and it has the same values as before. Okay. We're going to use A, additive. So so we could have, if we had no season, it would be in, and then A is going to be this changing seasonality. So the same way that we had the trend evolving, with the seasonal model, we have the seasonal effect. So what do I mean by seasonal effect? So think of like for the Chinook. So how much bigger, how much higher is the or June, July, how much higher is that than average? That's that seasonal effect. That year was a little bit lower than average. That one was a little bit higher than average. Okay, then we have the winter. This is lower than average. And you can see here it was lower than average by that much. And it's tending to stretch out here. Our winters are getting lower, lower. Maybe it's going down a little, but it seems like our winters are getting lower faster than our mean is. When we fit the ARIMA model with a seasonality, well, let's not talk about ARIMA model. Let's talk about like if we were to fit a model with a static effective season. So what we would do is we would take the average seasonality, which would be something about kind of like this, right? It's kind of not as wide as that and not as shallow as that, so it's going to be kind of in between. That would be the average seasonality. You can see for the Chinook data, that probably wouldn't be a really good approach. Another approach we could take is we could say, okay, well, we want the seasonality to evolve because I can see here that the winters are getting lower than average. So how about let's just use whatever we observed last summer or last winter. Well, that's maybe too extreme, right? We don't want to use that one. Maybe we should use the average of how much lower this winter is and how much lower that one is. So it's the same idea that we're using this weighted average of the effects of the season. And that's what the seasonal exponential smoothing model is doing. And the cool thing about this is that as seasonality changes, the seasonality in our model changes. And so it's able to track really dramatic changes in the seasonality. So what do I mean by dramatic changes in the seasonality? So imagine like this, like that. It's going to be able to track that. This is going to be able to track. It's going to be able to track, kind of random, things like that. All right, and so here's the example of fitting the ETS model to the Chinook data. And you see that warning there, missing values encountered using the longest segment, the longest time series with no missing values. There we go, produce our forecast. We can decompose. So here's our original data. Here's the level. You can see visually the mean level appears to be going down. You pick that up by eye, of course. The slope, okay, remember I told you this is cueing you in about the different sizes of the y-axis. So this is really big, so you go look over here. And it looks like, oh, wow, it's really changing. Wow, no, it's not. So the level is not changing. I'm sorry, the trend is not changing. The level is going slowly down. And look at this. The season, though, the seasonality is not changing. So what it ended up doing, if you looked at the parameter that affects how much weighting was used, it was close to 0. It was basically using the average season. What we could do is say, well, I don't like that. I want the seasonality to change. And one reason you might do this for kind of exploring is if you were curious about how these kind of seasonal peaks were changing. Do you see like all these little peaks here? And then we didn't have a peak there. And yeah, maybe the shape, well, the shape's pretty much changed, but maybe there's a peak here. And we are interested in looking at the weighted average and seeing how that peak is disappearing. And so what I've done here is I've said, okay, I'm going to set the gamma to 0.4. It's just like the alpha that you saw. Remember I showed you that plot with the alpha of 0.7 and how the weighting went down like that? 0.5 would be kind of weighting over the whole time series. So it's using some of the information on seasonality all the way out to the beginning here. Okay, now you can see that the seasonal estimate is evolving. Because that gamma is not equal to 0, it's a bit bigger. And so you can see here, we've got that hump, we've got that hump, we've got that hump, and now the hump is starting to disappear. And then here, it's gone. So if we fit a model with a gamma of 0.4, it would be tracking the more recent season more closely. Yeah?
How about the level and the slope have like the exact same shape?
The level and the slope have the, yeah, so, let me go, I need to show a plot here. Okay, so the level can model changes in slope also. So like if I told it to use a let's say I had no slope in it at all, the level is going to be going kind of up, and this is going to kind of track down, and then it's going to track down here. And now if I add the trend, I could kind of go halfway between that. So some of this drop I could say is due to a change in the level, and some of it is due to a change in the trend. So it's I guess it's basic. It's sort of the best. It's estimating the how wiggly the trend should be, and it's estimated that it should be a little bit wiggly, so that alpha shouldn't be really close to 0. And when you have that feature, that level is going to track this some. And so that's, like when I look at those decompose, do I have that for this one? Wait, try to get the decomposition without that seasonality in there. You can kind of see that same thing is happening in this one. It's not as dramatic here, but it's kind of the same thing. This is going down and this is going down. So it's explaining some of this by a drop in the trend and some of it by the change in the
Right. And then that precisioning is dependent on what your like exponential function.
Yeah, right. And that's kind of a hand-wavy explanation, but gets at the point that when you're looking at these decompositions, it'll give you a flavor of what's going in your on in the data, but don't like read too much biological into it. Okay, first that's that. Okay, and then let's see, are we okay? Good, yeah. So contrast this with the seasonal ARIMA model. The ARIMA model does the, will do the same thing. So here we go. In the lab, we'll compare these fits quantitatively. Right now, you can just kind of see it visually. They're different, definitely different. But the really dramatic thing is that the ARIMA models is not going to skip a beat with these missing values. And that can be obviously important to you if you happen to, for some reason, have missed a few readings. These are catch data. For some reason, there weren't catch estimates for these years, and you still want to create a forecast.